Hi, this is Stu Schwartz from MasterMathMentor.com. This is video BC02, and the topic is integration by parts. It covers the BC manual from pages 8 through 11. Suppose we were asked to find the integral of x cosine x dx. We take a look at all the rules that we learned in AB calculus. We had the constant rule, the power rule, the natural log rule, and the exponential rule. And x cosine x certainly does not fit any of them. We have trig rules that cover all different trig functions, but certainly nothing with x cosine x. And it certainly is not in the forms whose integral is the inverse sine and the inverse tangent. It seems that there's no way to take this integral, at least for now. When you learned your rules for integration in AB calculus, you may have thought it strange that there was no corresponding rule for the product rule. Let us work with the product rule and develop a formula for an integral. We start with y equals u times v, where u and v are both functions of x. Let's take the derivative of both sides. Since this is a product, we get that dy dx is equal to u dv dx plus v du dx. Now, if we multiply both sides by dx, we get dy is equal to u dv plus v du. Now let's integrate both sides. We take the integral of each term, and we get the integral of dy is the integral of u dv plus the integral of v du. If we move some terms around, we get that the integral of u dv is equal to the integral of dy minus the integral of v du. Using the fact that the integral of dy is simply y, for now ignoring the plus c, then we get that the integral of u dv is equal to y minus the integral of v du. And utilizing the fact that y is the same thing as uv, we end up getting the integral of u dv equals uv minus the integral of v du. This technique is called integration by parts. The integration by parts formula states that if u and v are differentiable functions of x, then the integral of u times dv is equal to uv minus the integral of v times du plus c. An integration by parts problem takes an integral of a product u times dv. In order to set up a problem with integration by parts, the best thing to do is to create a chart. The chart has four pieces, u and du, v and dv. You will fill in the u and the dv from the original problem, with the dx always going to the dv. From there, we will take a derivative to get du and an integral to get v. We will then apply the formula which will trade one integral for another. Let's see how that works on the next page. Let's start with the problem from the last page, the integral of x cosine x dx. Since we're integrating a product, integration by parts is called for. We set up our chart with the u and the du and the v and the dv. As stated, the dx will always go to the dv. There are several ways to complete the chart, but for right now we will put the u equal to x and the dv equal cosine x dx. We can now complete our chart. If u is x, du is simply dx. and we get that by taking the derivative. If dv is cosine x dx, then v is sine x. We now apply our integration by parts formula. The integral of u dv equals uv minus the integral of v du plus c. I sometimes like to put little arrows on our chart to show the u and v and the du and the order that we use them in our formula. So we end up getting that the integral of u dv is uv, which is x sine x, minus the integral of v du sine x dx. Now, when we take that integral, the integral of sine x is negative cosine x. So we find that the integral of x cosine x dx can be written as x sine x plus cosine x plus c. I like to encourage students when learning integration by parts to check their work if it's not too much trouble. When you take the derivative of your answer, you should get back to the original problem. So if I take the derivative with respect to x of x sine x plus cosine x plus c, we get, by the product rule, x cosine x plus sine x, and the derivative of cosine x is minus sine x, and the sine x's cancel, and we're right back to x cosine x. Let's look at the integral of x e to the x dx and the integral from 0 to 1 of x e to the x dx. Before we use integration by parts, we should be sure that we can't do this by another method. U substitution is indicated, but if u is x, then du is 1, and we cannot do this problem that way. So we need to use integration by parts. In our chart, we have 3 items that we need to place in the u and the dv. The dx always goes to the dv, but we have to worry about the x and the e to the x. It's trial and error. Let's put the e to the x in the u category and put the x in the dv category. So if u is equal to e to the x, then du is equal to e to the x dx. And if dv is x dx, then v is the integral of that, which is x squared over 2. Using our formula, we get that the integral of x e to the x dx is x squared over 2 e to the x minus x squared over 2 e to the x dx. And we are now faced with an integral that is far worse than the original one. So this does not mean that integration by parts does not work. It means that we made a poor choice in the placement of our x and e to the x. Let's switch our placement of x and e to the x, making u equal x and dv equal e to the x dx. Now our integration by parts formula says that the integral of x e to the x dx equals x e to the x minus the integral of e to the x dx. And it turns out now that we have an integral that we can easily take. The integral of e to the x dx is simply e to the x. So our final answer for this integral is x e to the x minus e to the x plus c. I leave it to you to check it by taking the derivative and showing that you get x e to the x. Now that we've taken the integral of x e to the x dx, the definite integral is easy. We have x e to the x minus e to the x evaluated from 0 to 1. Plugging in 1, we get e minus e, minus plugging in 0, we get 0 minus 1. And our final answer is 1. You may want to confirm this on your calculator. The process of integration by parts is really trial and error. You need to know which of the terms goes into u and which of the terms goes into dv. There's no hard and set rule. However, guidelines say that u should be an expression that gets simpler when differentiated, and dv should be an expression that is simple to integrate. If you follow those guidelines, you'll find that many integration by parts problems are relatively easy to do. In 3, we have the integral of x squared natural log of x dx. In setting up our u and dv, the best choice for u is the natural log of x because the derivative is easy. Du is 1 over x dx. The dv should be x squared dx because the integral is easy, x cubed over 3. So our integral of x squared natural log of x dx is equal to x cubed over 3 natural log of x minus the integral of x cubed over 3 times 1 over x dx. And that integral turns out to be the integral of x squared over 3 dx, which turns out to be x cubed over 9. So our final answer is x cubed over 3 natural log of x minus x cubed over 9 plus c. Verify by taking the derivative. In 4, we just want the integral of natural log of x dx. The choice here is obvious. Making dv natural log of x means that to find v, we'd have to integrate natural log, which is exactly what the problem is. But making u natural log of x, du is 1 over x dx, and if dv is simply equal to dx, then v equals x. Therefore, our integral is x natural log of x minus the integral of x times 1 over x dx. And x times 1 over x is 1, and the integral of 1 is x. So our final answer is x natural log of x minus x plus c. Again, verify by taking the derivative. Integration by parts problems can be tricky and difficult. Sometimes they will combine techniques. Sometimes it is necessary to use integration by parts more than once. Let's see some more difficult problems. Number 5 asks for the integral of x secant squared x dx. It's pretty obvious that the best choice of u is x because du is dx, and dv should be secant squared x dx because it's easy to integrate. V is simply the tangent. So therefore, we can write our integral as x tangent of x minus the integral of tangent of x dx. Now we know from AB calculus that we can write tangent of x as sine x over cosine x and use u substitution. U is cosine of x and du is negative sine x dx. So we can integrate that expression using u substitution. And our final answer is x tangent of x plus the natural log of the absolute value of cosine x plus c. Number 6 asks for the integral of inverse tangent of x dx. There's only one choice for u, and that's the inverse tangent of x. From there, du is 1 over 1 plus x squared dx. dv will have to be simply dx, and v is x. So our integral is x inverse tangent of x minus the integral of x over 1 plus x squared dx. This integral can be done by u substitution, letting u equal 1 plus x squared and du is equal to 2x dx. We can pull off this integration and get 1/2 the integral of 2x, 1 plus x squared dx, and therefore our final answer is x inverse tangent of x minus 1/2 the natural log of 1 plus x squared plus c. Sometimes we can use integration by parts twice. Here we have in 7 the integral of x squared e to the x dx. Best choice for the e to the x is in dv because the v is simply e to the x. And u is x squared and du is 2x dx. So our integral is x squared e to the x minus 2 the integral of x e to the x dx. Now this integral we did on the previous page. We did it with integration by parts, and we can see it done again. So we end up getting the integral of x squared e to the x dx is x squared e to the x minus 2 times x e to the x minus the integral of e to the x dx. Eliminating the parentheses, we get our final answer as x squared e to the x minus 2x e to the x plus 2 e to the x. And conveniently, we can factor out an e to the x times the quantity x squared minus 2x plus 2 plus c. In 8, we have the integral of x squared cosine x. It's best to put the cosine x in the dv category because it's easy to integrate. We get sine x. And put the x squared in the u category because it's easy to differentiate. We get 2x dx. So our integral is x squared sine of x minus 2x sine of x dx. To do this integral, we'll use integration by parts again. Again, the dv will be sine x, and v will equal negative cosine x. The u is x, and du is dx. So our integral is x squared sine x minus 2 times the quantity negative x cosine of x minus the integral of negative cosine x dx. And we can take that integral, so our final answer is x squared sine of x plus 2x cosine x minus 2 sine of x plus c. 9a is a tricky problem. We have the integral of e to the x sine of x. It makes sense to let u equal e to the x because du is e to the x dx. And dv makes sense to use sine of x because we can easily integrate and get negative cosine of x. So our integral of e to the x sine x dx equals negative e to the x cosine of x plus the integral of e to the x cosine x dx. Now let's concentrate on the integral e to the x cosine x dx. We will set it up the same way. We let u equal e to the x and du equals e to the x dx. We'll let dv equal cosine x dx and therefore v equals sine x. So our integral of e to the x sine x dx is negative e to the x cosine x plus, using the integration by parts, e to the x sine x minus the integral of e to the x sine x dx. Now, if you look at that expression, you have the same integral that you started with. So where do we go from here? And yet we are only 2 steps away from solving the problem. In the last statement, take the negative integral of e to the x sine x dx and bring it over to the left-hand side of the equation. So we're left with 2 integral e to the x sine x dx equals e to the x sine x minus e to the x cosine x. And since we are trying to solve the integral of e to the x sine x dx, all we need to do is divide by 2, and therefore the integral of e to the x sine x dx equals e to the x sine x minus e to the x cosine of x all over 2 plus c. Again, I suggest that you take the derivative of this expression to show that you get e to the x sine x. Sometimes we have to do integration by parts more than twice. And rather than repeating the chart over and over again, there's another technique that we can use called the tabular method. This method works well with integrals in the form of x to the n sine of kx dx, or the integral of x to the n cosine of kx dx, or in an integral of x to the n e to the kx dx. The tabular method involves making a chart with three columns: sines, u and derivatives, and dv and integrals. We first put in our u and dv as if we were doing regular integration by parts. Our sine column will alternate, starting with positive, then negative, then positive, then negative, and so forth. The u column will continually take derivatives. Since the u will probably be an expression of an x to a power of n, then the derivative will have a power of n minus 1, the next derivative will have a power of n minus 2, etc. Eventually you will get down to 0. And finally, the dv column is the integral of each expression. So we start with dv, and we take the integral of dv and take the integral of every expression in our chart. Next in our chart, we place arrows. First, a horizontal arrow between the sine and derivative column, and then a diagonal arrow down to the dv and integral column. We do this for each row. The solution will be a summation. It sums the product of the sine times the u and derivative entry times the diagonal dv and integral entry. Let's see this with two problems. Let's take the integral of x squared cosine 3x dx. This is definitely an integration by parts problem, and our u and derivative will start with x squared, and therefore the first derivative is 2x, second derivative is 2, and the third derivative is 0. We can stop there. The sine column will be plus, minus, plus, minus. The dv in integrals will be, starting with cosine of 3x, the integral of that is 1/3 sine of 3x. The integral of that is negative 1/9 cosine of 3x. And the integral of that is negative 1/27 sine of 3x. So, using our formula for the tabular method, the integral of x squared cosine 3x dx is x squared over 3 times the sine of 3x plus 2x over 9 cosine of 3x minus 2/27 sine of 3x plus c. A good exercise is to take the derivative of this expression and show that you get back to x squared cosine 3x. In 12, we're asked to take the integral of x cubed e to the negative 2x dx. Our derivative column will start with x cubed, go down to 3x squared, then down to 6x, then 6, then 0. Our sines column will be plus, minus, plus, minus. And finally, our dv starts at e to the negative 2x, and if we continually integrate, we have negative 1/2 e to the negative 2x, 1/4 e to the negative 2x, negative 1/8 e to the negative 2x, and finally 1/16 e to the negative 2x. Since all the terms in our sum have a common term of e to the negative 2x, we can factor that out. So our integral of x to the third e to the negative 2x dx is the quantity negative x to the third over 2 minus 3x squared over 4 minus 3x over 4 minus 3/8, and that quantity is multiplied by e to the negative 2x plus c. Again, a good exercise is to take the derivative of this and show you get back to x cubed e to the negative 2x.